Just give me a moment. I just need to change the permissions, I presume. Yes, I need to share the permissions. Give me a moment.
Sankalp. And
Okay, is it visible now? Nope, I guess nope.
UPI.
Can you see my screen, by the way?
No.
Oh, thank you.
Near the speaker icon, there is a open share tray.
Yeah, actually, that's the weird thing. So I should just give me a second. Maybe I need to refresh my screen. BRB.
Okay.
I think my screen should be visible now.
Yes, it's visible now.
Perfect.
Okay. So we'll start in 2-3 minutes.
Yeah, sure. On your mark.
Okay, so dear all, let us start. And we have a young and talented student, and who is now his own startup he has initiated. So is with us. Is meet with Sankalp Ghatpande. Is a researcher and engineer with over 7 years experience in working on different research projects in academia and industry. Is currently co-founder of CheckMath. CheckMath is a tech startup, and he is also a freelance consultant for two firms, primarily based in Luxembourg. So he has shifted to Luxembourg for his master's after completing his studies over in India, and he's primarily working in security, cryptography, and as a data analyst. He has been part of multiple European Union-wide projects, including Biotope and Athena. In last year, he has been working on software engineering research that specifically focuses on code search and code analysis using machine learning. He is also an active contributor to multiple open source projects and standardization attempts for protocol as a member of ISO group. And as I said, is a young talented guy who has established himself in Luxembourg. Luxembourg is a small country where he has been identified and he's been treated as a very resourceful person, and he is giving services to many IT industries as well as to government of India also there. So he is a very enthusiastic, very prominent, and very promising guy, and I am happy that he is going to share with us very advanced tools for data processing. And we all know data mining and data science is going to give good results. Machine learning gives good results if the data that we have is very pure, the data is very good. Today only morning I saw one very good cartoon where everyone is running for data science. There is a very big mob and one man is asking who want data science. So everyone is raising their hand. Then he says, "Oh, who has data?" And then everyone has putting their hands down. And then the last one was like, "Who can label the data?" The person asked, "Who can label the data?" And it's like it's a supervised learning. So who can label the data? And all the mob has gone. So everyone want data science, everyone want machine learning, but the actual work that has to be done with data. So there are tools now available. It was like a headache. So I'm happy that Sankalp is here and he can give insight into that one. So I request Sankalp to start his presentation.
Yeah. So good morning, everyone. Well, good afternoon to you guys. It's still morning for me. So just before I begin, I'm just going to paste in the chat a quick link. It consists of all the notebooks that we'll be using for our talk. So basically to support it and walk through. Don't worry, you don't have to go through it alone. We will go through it together. So first, thank you very much, Professor. Oh, please.
And Sankalp, like your voice is little low. Like you can increase your volume also.
Yes, just give me a second. Let me just check. Hello, test. Is it better this time?
Yeah, it's now good. And like you are from the war front, I was telling to the people like he's from Europe and from the morning it's like when they were sleeping, Russia has attacked on Ukraine. So maybe.
I mean, we didn't celebrate that, thankfully, but it's.
That's right. So maybe your accents are now European, so you may be little slow when the speed of speaking will be. If it is slow, then
Yes.
it will be better for us. Thank you.
Yeah, please. In case I'm fast, please interrupt me and immediately inform me, because I am now used to talking a bit fast, so might be issue. Even I don't realize it, to be honest.
Yeah, with the participants are like it's advice for, and you can also interrupt him to Sankalp.
Please do. I'll be really happy if you do. In fact. Okay. So firstly, thank you very much, Professor Joshi, for the introduction. I'm really honored to be here to give a talk. So as Professor Joshi mentioned that I've been in Luxembourg. I've been working as data analyst, data scientist actually, for a big bank here, BNP Paribas, which is one of the biggest banks in European Union. The biggest thing I realize is that machine learning, as we know, is not that simpler. It's not like just going in, deploying a model and getting the output. The problem is that there is data that we don't have any knowledge about. As I mentioned, the cartoon, it perfectly fits in that we have too much data, we don't have labels, or we can use unsupervised learning, but still, it's like there's too much data, we don't know which feature to use or how exactly to visualize it. For us as a data scientist, we can understand what the data is. But if I want to show it to my management people, the people who would actually take the decision like directors, it will be really hard for them to understand. And that's where we use the tool or the thing that we call as data visualization. Visualization is, of course, the most powerful thing that humans have. If we can see things, if we can measure them from our visual eyesight, it has a bigger impact. And that will be my talk, in fact, that okay, so we have data, we can visualize it, but even that data can be gigantic. It can go to billions of data points, items that we are inside it. But how do we exactly reduce it in a way that we can visualize it? Human vision is, of course, limited to only three dimensions. We cannot go further from that, which means we should be able to represent the data set or data in a way that our eyes can easily understand. And that will be my talk. Basically, going for dimension reduction, which means reducing thousands of features to something that is more compact, understandable, and visualizable. And for this, something that I realized during my job that I do as a data analyst is that we have a kind of misconception. What exactly should I use to have data reduction? As we all know for sure that there are too many techniques. There is manifold learning. There is also projection-based learning, each of which have different techniques inside it. We have PCA, TESNI, UMAP, LDA, SDA, and I don't know how many of them. And that's what I will focus on. Try to understand how we can have the data reduction using code actually, so that we can actually see them in live action. And finally, try to answer a question that has been plugged many of the industries, including one of the startups that I work for, that which data reduction technique should I use? Should I go for PCA, TESNI, UMAP, or LDA, which are the most prominent one? So let's begin. Oops. Oh, yes. So before that, a short introduction again. So as Professor Joshi also mentioned, I've been working over 6 years as a I have research experience, both in industry and academic. My topics have been practically a lot of them. I have mostly worked in cryptography, machine learning, and data analytics. But I have also been part of projects that focus on Industry 4.0, or IoT, as we know, blockchains and software engineering. Currently, I'm a co-founder of CheckMath, which is an education startup that helps students get feedback on their mathematical steps. For this, we have designed our own neural network, feedback-based neural network. The other one is that I work as a consultant for iWarranty, which is a fintech firm that focuses on using NLP and OCR to understand the warranty terms and provide it to the user in an understandable way. And of course, I'm also a cryptographic developer, which is my passion, in fact, for consulting firms here and also abroad. So what are we exactly aiming in this talk, or rather what I learned as a part of my work? Because when I joined as a data analyst, it was really hard for me to go ahead and actually provide them results without myself understanding what was it supposed to be. And this talk basically follows what I learned from my 2 years of experience at the bank. Now, we have, as I mentioned, that I have worked at one of the biggest banks as a machine learning and data analyst. The problem was there was just too much data, too much as in there were billions of customers. Each of them have a KYC that was fine-grained to a finest detail, including where they stayed, their houses, their family details, the other things such as their ID cards and so on, which means there were too many features that I could leverage to understand or to generate my own model. The key, of course, was the visualization in this case, which is that I can actually visualize the features and show it to my director, who I was directly reporting to, that look, we can use this feature, this will provide us this information or not. But the problem was the data was too big. If I tried to fit it in any of the normal algorithms or normal approaches we have, it was too big. And that's where I suffer from the curse of dimensionality. Now, what is it? So in this talk, we'll be talking about, of course, the curse of dimensionality. I will give a small explanation of that. What is exactly the dimension reduction that we go for? Then we will focus on the popular approaches. Just note that I will try not to focus on the mathematical aspects of the talk. Rather, we will jump in the code and see live action so that we can actually visualize it, including play it ourselves. And to do this, we are going to choose the MNIST sign data, which is the sign language data that is available on Kaggle. Of course, when we go ahead, we can also try on another data set that are there. So what is the curse of dimensionality? As we all know that machine learning problems involve thousands, if not more features. Or if you go for deep learning, it even goes to billions nowadays. For instance, if you look at the AI engine that was developed recently to play the Go. Oh, yeah. Any question? Sorry, I thought there was some question. So the Go, the board game, it had almost 3 billion features that were trained on the model before it was being usable. So as you can imagine, it goes like exponential as we go ahead. And that creates some major problem. First, it makes training extremely slow for us, which is of course not something we want ourselves to be stuck in. We don't want our model to run for 2 months and then we see it has not learned anything. One, it makes it difficult to find a good or even a reliable solution. Recently, we have been working on a software engineering case where we try to find actually out of distribution data from a data set. For this, we trained a model. We let it run for 2 months. After that, we realized that it was not even learning anything that we consider as a definition of out of OOD in the data set. So that is in fact what is cause of dimension. And in fact, the magazine that is by the Scientific Marketer is in fact catching it perfectly fine, that we are doomed if we don't know that. And the only way we can do it is, of course, looking into the data rather than looking for more data. So what is exactly the dimension reduction that can be applied to reduce the curse of dimensionality? Well, it's a process of reducing the number of features to relevant one. As an example, let's say we take the data set of our current people, participants who are in the talk. We are around 60 people, let's say. Each of us has different details. We have different gender, different age, different locations, different education, different languages as well that we learn. And if you try to use all that information in order to understand the model, it will be complicated because everything is different. Some of them are irrelevant. For instance, we do not care where we are. We all are in the same field, so we can remove that. And that's where the dimension reduction can come in, where it tries to compress this 7th set of features to 2 or 3 set of features that can visualize or even use. To think of it in an intuitive way, think of dimension reduction as the same as compression that we do. We zip our folders and everything. We do the same thing, we compress everything to a more manageable level. The advantages, of course, for dimensionality reduction is that it is faster, because when we have a less number of features, we can train faster on our models. And it also filters the noise. As an example, when I was working in the bank, we were working for a project that required the overdrafting. I'm sure every one of us knows it, that whenever we have an account, business account, and we want to use more than what is in our account, it is called an overdraft. What they wanted is to automate this feature, which means they didn't want a human to look through, is this person eligible for an overdraft or not? Rather, they wanted a model that would make a decision whether it should be directly given or granted or not. The thing was, there was too much data, as I mentioned, for the account. And when we went for the dimension reduction, we realized that it was actually also trimming the information that was not there, which is filtering the noise, in the sense that the people who are never going to or had never used overdraft facility, they were automatically trimmed out from our data set, which made it advantageous. The disadvantage, unfortunately, is the loss of information. Remember that data is the new oil, as we all say nowadays, and every point of the data set is just as important as the other. As I mentioned in our example of the participants here, we don't care what our education was because we are all in data science. But if you want to map out, for instance, some may be on the applied side, some may be on the theoretical side, then we would need this information. But if you happen to apply the dimension reduction, it may be removed from that. And this, of course, directly implies the performance, that we lose the performance here because we lose the key information that can be useful. So dimension reductions have multiple applications. The first one, obviously, is the data compression. For a data set that can be, 1 gig, we can compress it to a level of at least 400 to 500 MB, which is almost 50%, depending on what you use, of course. We also reduce the noise, which is obvious. Then we can also have some sort of data classification, because when you reduce the dimension of a data, you actually also make a similarity between different data points, allowing you to have some sort of classification or clustering of the data. And finally, the most important is the data visualization. The data visualization actually makes use of all the other applications itself, because for visualization, you have to compress your data in array form, or at least a form that can be represented. You reduce the noise. And of course, you classify the data, because that's what the visualization is about, to be able to classify the data. So the two important things about data dimensionality reduction is that it is the most important aspect that is currently used in data visualization everywhere you go, even in industry, in academia, even in our research, in fact. And dropping the dimensionality to 2 or 3 makes it feasible to visualize. Of course, we can always see the dimensions in 2 or 3, or even visualize it using multiple tools we have. But imagine you having to do it in the 7th dimension. It would be extremely complicated. An example for this, if you're curious to know, is to go for manifold learning, but not on the normal one, go on the topological field, where it is really hard, where you have dimensions that go more than 4. It is really hard to even imagine how it looks like. You must rely on mathematical and aspects there. So before we begin, just a quick set of questions for everyone so that we can then decide how we should go ahead. How many of you are completely familiar with Matplotlib, Disney, UMAP, or other information, other things? Just a quick write down should be enough in the chat. And don't hesitate to say no, because even I was not familiar with Disney or UMAP, for instance, when I started. The only reason I'm asking this is that if not many are familiar, then we can go through the basic notebooks immediately, just as a revision, refresh for myself as well, to be honest, and then we can jump to the advanced topics. Hello. You can also voice it actually if you don't want to type it in. If not, then I will go through all of them actually. So just a 1 minute of call, heads call. I will take that we'll go through all of them. Should be fine then.
Yeah, we can visualize once we come through one example. So being beginner, we have to actually see the dimensions. How is it really difficult to visualize? Then we can think of reducing it meaningfully. So let's see.
Okay. So let's do something then. We can go through all the basics actually. I mean, just to refresh the knowledge. And then in case there is something that is missing for anyone, you can question and we can dig deeper in this case. So I have already pasted the notebook link on the chat we have. And here is another notebook that we will be using. Oops. Just to go through the basics. And let me just change my screen share so that I'm sharing everything now.
Actually, we don't have access to the chat box. So that's an issue.
Oh, oops. I'm really, really sorry. Professor Joshi, how should I share it then? Would it be possible for you to note down the URL here, please?
Yeah, we can do that. Yeah.
Perfect. Yes. That will be perfect. Thank you very much. And the other one that you can note down is, I'll just paste it on the Colab that I'm currently opened. So this is the link. So I would like everyone to go there, and I cannot share the full screen for some reason. Oh, now I can. Oops. So this is the repository which contains all the notebooks that we'll be going for. So first, I would really like if everyone can go to the supporting notebook. So you have the main repo, visualization workshop. Then you have the source, the supporting notebook, and the matplotlib, the first one. You also have a link directly to the Colab. In case you want to do it locally, it's fine. Just clone it out. If not, you can click on the Colab, and it will direct you to the Colab one directly. So I will continue in this case. Everyone can see my Colab screen, correct? I guess you can, right?
Yes, sir.
Oops. Perfect. So let's start with a quick recap of all the basics so that we can understand the code as we go ahead for PCA, Disney, and UMAP. So first one is, of course, the matplotlib. So matplotlib, as many of you know, is one of the most famous and, in fact, powerful library for creating not just static, but animated and interactive visualizations in Python. It is, in fact, I'm sure many of you have already used it when you had to visualize your results when you're making a publication. So let's go through it quickly. Of course, we import our matplotlib as matplotlib and plot. And the most important thing whenever we visualize is, of course, understanding what a figure is. Oh, pardon?
A little bit louder, sir.
Yeah.
Your
sorry. I think the settings kind of get messed up. Just give me a moment. Let me just increase the voice maybe. That's already full. Can you hear me now? Better?
Yes, sir. Yes.
Hello? Yes, awesome. So the first thing, of course, is that we should be able to understand the figures that we're visualizing. So here's a perfect example, actually, that has been given by matplotlib themselves, that we have a figure. We always have a title. We must have a title for the correct representations. We, of course, have the legends to define what exactly is the plots that we have. We have the major ticks to define the axis on the X and Y axis both. We have the labels for the axis, the major ticks and the minor ticks. We have the different type of plots, the grid lines if we need it, scatter plots, of course, which are dots, the line plot, which is normal gradient line, the axis, and finally the spines, just as how our graphs or plot should be. Now, the next thing, just to quickly walk you through the code, is that, okay, I forgot to run the first one. Is that, let's see how a normal plot looks like, how you can define a normal plot in the matplotlib. You can define your range. So this is a sample. I'm doing it 100 by 100. I just plot it with a normal gradient line, nothing else. Similarly, we also need to be able to plot the axis and figures for each of them. So here we can define our sine and cos signals, just a normal one. We can plot them one by one. So this is our sine one, this is our cos. But of course, this is something that is separated. If you want to overlap them, which is what we will require when you're doing the data visualization, is to see them compared to each other. We can plot them together. Just put in the plot.show at the end of your plot commands, and it will show you them mapped in the same figure. Now, of course, the important thing is, as we have, that we should be able to caption the figure. We should be able to also add the subplots inside it and also have the access for it. So for that, we can just define the subplot, add subplot as a command, and put in whatever we want within the axis, and it will put them as a two separate plots within the same one. The color C is, of course, a shorthand that is used for color to define them, and BAG being the blue and green that we use as a shorthand again. Similarly, when we go for data visualizations, we may have multiple data points that we want to signify being different from the other. The color is obviously the most obvious one to do that. And for that, we can either use, of course, the color one that I mentioned here, C, or similarly, we can define it as a hex code as well, if necessary. So it will show us as a hex code.
Can its font size is increased, like it, or otherwise
yes.
you can zoom in? Zoom in, maybe.
Good.
Yeah, it's better.
Perfect. Yes. Thank you very much. I was not aware how the screen will be for you. So for the color as well is the same. We can define it as a hash and or either as a color, or we can do it as a C or color. It will be the same one. Now, it may be the case that we have multiple representations of the data, each of which signifies something else. Just having the normal line may not provide us with the information. For instance, if we want to show a trend within our clusters, we will have to, it would be better if we can show it as a dashed or dotted line. So for this, we can just as a line style or as a shorthand ls and provide what we want. Of course, the legends are important because this graph provides no information of what is each of them. It is just a line for me. I cannot find much information on it. For that, the same thing, we just have to provide with a title, and it will provide us with a kind of title legend that what it is about. And of course, I'm sure many of you already are aware of LaTeX that we use to write our academic paper. And if you want to export our figures to that, it's better if you write it in LaTeX so that it will be compiled and look much more integrated within our papers. So for that, Matplotlib is pretty generous, let's say. It directly allows you to provide your LaTeX inside your normal $sign. So for here, I can just provide it with my equation. It's perfectly fine, works normal. Similarly, I can do it also for the with a subscript of as I do in the LaTeX, while keeping my normal text in the UTF format as a normal one. Then, of course, we have also another thing, which is that we would like to point out what each of them means, which means the dotted lines must imply something, while this one implies something. For this, we just have a dot legend as a parameter that we can provide to our plot with the information that we want, which is LOC is where it is located. What is it supposed to be? Fancy box, which means it will be in the box one. I want it to be with a shadow. And when this happens, whatever label I give to my plot, it will be written down there. It will be printed out. Simple as that. Then, of course, we have another thing that we want to also show the grid lines, because grids are sometimes important to interpret the results, especially if I have a big one, I want to see where the line lies. Then all we have to do is just set the grid to true with the information that I want. I can set it as a dot if I want, how much should be the spacing between them, between the lines, I mean, and how much should be the length of it. I can just define it and it will be printed. Simpler. And of course, graph representations comes in different format. We just saw a normal line graph, but there can also be different ways of representing our data. The most important or most well-known of which is the scatter graph, which we use in data science. So for this, all we have to do is just change our plot from the earlier one to scatter with the information of our data set, which is a random array that I generated here, and the second set of array that we want against whom we are comparing it, what should be the color and what should be the marker. That's it. We have our scatter graph ready. Then, of course, we also have that we should be able to control the area. Sometimes we have a data point that is influential to the other. For instance, let's say we want to show a geographical location of certain population, then we want to be able to show it as a more, let's say, influential radius. Then all we have to do here is that provide the area within the scatter plots parameter, and we should be and we should be able to show it as this area. Similarly, we of course have the bar chart. We have the bar chart, which is the normal chart that we know. For that, all we have to do is of course part in the dot bar parameter. The others, I won't go through that because we do not have time, and plus they're not something that are more useful to us at this point. We are mainly concerned with the scatter graph, which we'll be using for our experiments. So let's start then. So first one is of course the PCA. I hope everyone can see the screen. Yes. Yeah, I think it's sharing. Perfect. So PCA, as we know, is principal component analysis. The goal of PCA is to reduce the dimensionality of multidimensional data. Remember this keyword that it will only be useful for multidimensional. If you accidentally happen to try it on the linear data, it will mess up. It won't show you any relevant information. The principle of PCA relies on linear algebra, which is the method of finding the axis with largest distribution of variance and finding it and projecting on the second axis that is diagonal to that. As an example, let's say this is our first dimension. If you're looking for your data, it will always be plotted as a gradient of it with respect to the other quadrant or other dimension in this case. It is, of course, easier to preserve the variance in the raw data. What it does is that it tries to find the eigenvalue and eigenvectors in the matrix format and maps it out, which makes it easier to find which one is how much is the variance between each other, and to find the orthogonality of the axis between the data points. The difficulty is, the difficulty in this one is to interpret the generated two axis, as we'll see in our example. The disadvantage is that the cluster data gets crushed as the dimension is reduced. Just imagine that the example that I was seeing about the number of participants. If you try to use that and use the PCA on that, it will actually crush all the dimensions to 2 dimensions, meaning that even if there is a dissimilarity between me and some other data point that is there at the participant, it will not be easily visible. So let's start with a quick example. We do our normal imports, which is that we import the NumPy for numerical operations, pandas because I want to read the data set, matplotlib because I want to plot it. And this is the import warning. It's just so that I will ignore the warning that Colab does, because I have run it on my local GPU, which differs a bit from the Colab, but it still runs fine. So let's set up some parameters so we can visualize our results. The first one is that I'm just setting that our image, our graph, should be in grayscale. Then I'm setting the R color graph. So what are the colors that will be used for each of the data points that are there? They will be assigned randomly based on the data points we provide. Now for the data set here, I'm using the MNIST train data set. So this is the data set for the pixels, for the languages, numbers, and everything. I'm sure most of you are aware of it. Oh, I accidentally ran it again. We need to wait. Yes. So we have a data set with label, what it implies, the pixel of each of of how one is represented in different ways. So overall, we have 5 rows here in this case, and overall 785 or 784 if you start from 0 number of features that in which we can represent a number. So let's be a bit simpler because we are going for PCA. Remember, PCA is something that works a bit on unsupervised. We don't need to have labelings here. I'm just going to drop it out. So we drop in our labels, and that's it. Now that we have our data set cleaned out, the data cleaning or pre-processing step, we now have to convert or understand what exactly our data set is. So for this, I'm creating just an array. We are taking as an input. This is just a function that will call through that converts it into image for us to see. I'm just iterating over the data set we have and plotting them out. So this is basically the set of data we have, with each of them representing a certain number. Let's go for PCA. So PCA library is prominently found in the sklearn library of the Python. It's most of the time installed on majority of the distributions nowadays. If not, you can just do pip3 or pip2 install sklearn and it will install it. So we install from sklearn decomposition, we import the package called PCA. For PCA, we set the n component. So n component are the number of components that we wish to visualize, which is 2 in this case. And we fit it. Fitting, of course, I won't go into the problem of overfitting because that's completely different parameter. But we need to fit our data within as a PCA, as a dimension. So we fit it. And finally, we make a transformation of the original data set to the PCA one. Once that's done, all we have to do is basically plot it out. So what we do here is that we iterate over each of the output that we have from a MNIST PCA and provide it to the scatter graph as an input. And for each of them, I basically just put it as a result and map it out. So what we get in the end, can I zoom out here? I will just zoom out, pardon me for a moment, so that it is easier to see the result as a full. So this is what the PCA shows, that we have 0 to 9. Each of them is clustered around but it is really hard to understand what each of them stands for. For instance, this is, I don't know, perhaps 2, yeah, 2, and here we have 7. It's not exactly a useful graph because it's completely messed up. It's in the sense that it's completely decepted, so we cannot understand what it is about. And it is a bit slow, but that's fine. So moral of the story is that PCA, we cannot rely on that to understand what our data is. It's too low, too slow as well, as you can see, and it's too cluttered out. It's not possible to visualize the data, which means obviously that PCA is not the ideal choice that we should go for. So let's go for the next one, which is the TESNI. The test, yeah, you can see. TESNI is the T-distributed stochastic neighbor embedded. What it does is that it tries to find the, it maps all the data points you have as a Gaussian distribution and finds the Euclidean distance between them. Do note that by default, it does Euclidean, but there have been variations of TESNI which have used different distances, such as the Manhattan one as well, with varying results. For this talk, we are going to focus purely on the Euclidean one. So what TESNI does is that it determines a reference point, which can be random, or you can set it as a seeder for yourself. Then the Euclidean distance from this data point to all the other data points are calculated and mapped as a Gaussian or a normal distribution. And this distribution is expressed as a probability whether it belongs within the correct cluster nearby to the data point that you selected or not. Based on that, it uses what is known as a KL divergence as a cost function. I'm sure everyone is aware what the cost function is, for learning the gradient descent as an optimization method or optimization process. The main thing about TESNI is that it preserves local neighbor structures, which means if you have 2 data points that are closer to each other for certain features, it will preserve them rather than reducing them in case we have more other features that gets added. However, if you increase the number of data, it may take a long time, of course, because the computation goes square x. So it increases by O to the power of n square complexity, which is not optimal, especially as you have n by n, because you have n of the data set compared to the n square that you're going to check against. It is extremely slow in speed in terms of speed, but pretty good in terms of clustering for performance, as we'll see now. And recently, in fact, something that is really good is that, as you all must have heard, that Apple recently developed a special chip they call as M1, which uses their own neural network, and they're specifically optimized for TESNI, which means that potentially in the future, we might even be able to do it much faster than what we are, and may have better results as well. Unlike the PCA, which was, I remember again, unsupervised, this one, oh, sorry, TESNI is supervised learning. So let's start with normal one. We do the same thing again. We import our NumPy, Panda, Matplotlib. We ignore the filters. We set up the parameters that we want it in the grayscale. Grayscale only because I am not much fond of colors. And we set in some random set of colors that we'll go through. To read the data, oh, okay, there is a problem here. To read the data set, I have already uploaded on the repository, the MNIST train. So I'm just going to call it out. Similarly, we'll also strip the label, column, because we don't care about it at this point. To import the TESNI, remember, PCA is the only one that is on projection based because it directly projects the data that you have. TESNI, on the other hand, is manifold-based learning. So manifold-based learning basically means that, let's say this is your plane, you have your data points here. Rather than just pointing them here, it tries to make a manifold up, which is fold it out in order to see the similarity between them based on the domains or dimensions that are there, which is why we call it as a manifold-based learning. Here we do the same thing, of course. We import from sklearn, which is a perfectly good library. Actually, I would highly suggest you to use that. There are some other libraries, but I'm not familiar with them. We import the manifolds under which we have the TESNI. For TESNI, we do the same one. We define how many components we want. Components can be thought as another way of representing the dimensions we want. So 2, and the random state is set at 0. The random state is a seeder. So if you set it as a value of 2, for instance, and next time you provide it with the same set of data set and the same random state as 2, then it will always give you the same set of results. It's a way of allowing reproducible results, nothing else. We do the same. Oh,
you need to zoom it again.
Oh, thank you very much. I think it's because of my monitor, because I'm on 11 inch currently. Sorry. So we do the same thing again. We, of course, put our graph. We map it correctly, and we map it directly as a scatter graph. Using the same function that we have, we don't change anything. The only thing we change is, of course, that the consuming is MNIST here. We don't consume anything else, and that's it. And here we have our first TESNI result, as opposed to what we have as a PCA, which is here, which is completely cluttered. We have no clue what is what. This one provides a bit better information in the sense that at least we can see that 0 is completely here. Of course, don't forget that we still do have some errors. For instance, the 2 here in the 2 does not belong yet, but compared to the PCA, it still provides some valuable results for us as a first step towards the clustering. So that's for the testnet. But still, we have some errors here. How do we exactly go away from that? Because I am pretty sure that all of us would like to have a clean output, clean cluster that we should be able to see. And that's where the people came up with a new approach, which is called UMAP. So UMAP is Unified Manifold Approximation and Projection. So as I mentioned, the manifold projection basically means that you collapse your plane onto two. As you must, to give you a quick example on that, you remember Einstein mentioned that his space-time relativity theory says that we do not belong in the same plane. Rather, the plane is folded onto each other. It's the same principle that it follows, following on the topology, mathematics of topology. The change here against testnet is that when it is used for visualization, testnet, remember, it tries to keep it constrained in the sense that it tries to remember what are the data points close to it. UMAP does not restrict within the size of the dimension either, which means that for UMAP, you can provide it with gigantic amount of data and it will still try to apply the dimension reduction with a wide set of success. To provide you the example again on what I learned on my job, when we were in the bank, we had customer data, of course. When we tried testnet, it was absolutely useless because there were customers, for instance, like me, who is an Indian, who studied here and now is currently working here, but I still come to India to do my economic and everything. I mean, spend money and so on with my family. So when I'm there, it will always point me to the another group of the clustering. Why? Because it does not see this as some sort of feature, which is something that UMAP does not consider and provides a much better result. The main thing about UMAP is that it does not care about local structure, which is how close I am to the data point is not considered if I'm closer to some cluster on a global level. That is what is much more important for UMAP. It is based on a solid theoretical background. It is based on Raymond's geometry and topology, something that I don't want to go in detail with because maths is not good for the mental health sometimes. But I urge everyone to go through the paper. It's a brilliantly written paper, well understood as well. If you skip the mathematical detail, it's still understandable. So let's begin. Give me a moment. I think I should magnify this, yes. So we do with the pre-imports again, the NumPy, Panda, and everything as normal. The configuration we keep the same. We don't want we want to have a clear comparison between each other. Now for the data set, we do the same. We use the same data set that we have. We have the same features, of course. And here as well, I drop the label because I want to keep it as unsupervised as much as I can. And here we have it without anything, which is we have 784 or 783 if we start from 0 features. So let's begin. The thing about UMAP, something really, really important for everyone, is that UMAP does not come with a normal library, so, which means if you do pip install UMAP, it will install a library that is not UMAP. So to install it, make sure that you do always a UMAP learn. Just run all. You need to do a UMAP for, yeah, that's fine. You need to do a UMAP learn, so it will install it. Even if you're using the Colab, make sure that you install it because it does not come default. Then, of course, we have to import our UMAP. We do the import, and UMAP has what is called as a reducer. Reducer is basically that if you have multiple dimensions, so this is one dimension, you have, let's say, hundreds of those stacked over each other. We want to reduce those dimensions in order to be able to understand or visualize our data. So in this case, the reducer, we make the UMAP to a random set of 42, and we make it to fit transform to our data set. It will take a bit of time, unfortunately. Unfortunately, UMAP is a bit slower because it has quite a lot of processing, GPU processing that it requires, but we can go ahead meanwhile. Similarly, as we did last time, we are just going to import all our data and put them in the scatter graph so that we can see it. And now we just have to wait, unfortunately, for it to finish. This one is not okay. I'm also putting in the time for each of them so you can actually visualize when we come for the final notebook we have, where we can actually compare the timing between each of them. And something that is worthwhile to see is, of course, that UMAP takes the highest amount of time as opposed to others. The time taken is obviously because it has to go through each of the dimension, fold the dimensions, and see the relation between any data point to the other global structure that is already established. Yeah, this is something that is a bit bad about UMAP, but maybe I can, while it's compiling, I can directly show it to you on the saved states we have. Oops, it did not load. We'll come back to this one while it's compiling then. So let's get back to our presentation in this case. Is my screen visible actually? Can you confirm that you can see my presentation?
Yes, sir. Yes, sir.
Perfect. So I will quickly run through what we already saw on the code, and then I want to have a comparison between them. So in the UMAP, we will obviously have some results, which will be, oh, we are done. Perfect. So let me zoom out a bit. You can see this is the UMAP with the same data set, and we have a much better results, much better in the sense that they are a bit cluttered. They are clustered with a pretty much higher set of distance between each of the clusters. They are not closer, which means with confidence we can say that this data point and this data point are completely different. While on Tesla, it is hard to say if they are different because they are close to each other. The Euclidean distance means that they will always be close. The thing about, I mean, I'm pretty sure everyone has a question of why we still have some points that are there. And this is the reason how the data set is. For instance, we can write 3 and 2. They can be close, similar to each other, which is why it classifies it as being similar. This is the reason why they are closer. But it's still close enough to what we have as opposed to Tesla, where we cannot exactly divide them into different sections. So now that answers our question about what is a UMAP. But still, the main question lies, what should I use or what should you use if you have a problem or if you have a data set that you want to visualize? So let's do an experiment. We already did it on the MNIST
I
data set.
have a question.
Yeah, please.
Can you go on to that visual representation?
Yep.
Like, say for example, if you pick any point, it's like its dimension is reduced. Actually, it is a multiple dimension point, but it is now reduced only to 2 dimension.
I will correct you a bit here. It has been reduced to 2 dimension only for the visualization, but its features have been written to number of dimensions that were there, which means, let's say we take this point. Oops, I should not have zoomed. Okay, let's say if we take this point, then this point, which is 8, I presume, it's 5. So 5. So it still retains its original dimensions and features, but only for the sake of visualization, it has been compressed and reduced to the dimension. That's the magic of the UMAP.
Yeah. So we are actually still have 8 dimension data.
Yes.
And it's represented as if it is a 2 dimension data, so that we can visualize it and we can understand it.
Yes, indeed, correct. Visualize it, understand it, and also be able to understand why some data points are closer to other cluster than other. For example, if we dig deeper in this, which we can do if we have time, in fact, if we dig deeper in this data point, we can visualize it, and we will see, in fact, that it actually looks closer to this one than its original number, which is this 8 looks closer to how 1 has been written or generally in the data set, which is why it is here. Does that answer your question?
Okay, no, it's fine, but it's again, this one is again based on distance. They are closer, and like say Euclidean distance only they are considering.
Yes, this one considers Euclidean distance, but it does not consider point to point. It considers point to cluster and then point to point, which means, let's say you have 1 point here and 1 point here. This is your plane. It folds it and tries to see first the distance between them. Then it groups each of the cluster, and sees if this point belongs to this cluster or this cluster. Then whichever one has the lowest distance, it shifts that data point to that cluster. So you can think it like a fitting problem on the multi-dimension.
Okay. But actually, it doesn't reduce the dimension.
Yeah, that's a bit kind of technically, let's say, middle ground here. It does not technically reduce it for visualization, but while it is doing the clustering, which is when it is trying to fit in, it does reduce it, but only for temporary. It still tries to retain as many dimensions or as many features as it can. Maybe we can hold us this question when we do the comparison with each of them, because I think that will be much more easier here. So, I mean, sorry for that, but I mean, I think it will be easier. I can understand the confusion, but we'll get through it.
Okay.
Okay. So, as I mean, the question is that what should we use for the data point? Because we saw it in the 2D dimension, it looks fine and everything, but there are still some things that we need to get through and understand. So for this, we are going to go through a small experiment where we'll use the MNIST data sign data language because it is smaller one, and I do not want to burn the GPU credits that I have for the Google. So let's start with that. So what is the PCA? As we already said, that it works by identifying the hyperplane that is closest to the data and projecting on that as a variance of the data set. We already went through this, that this is the principle of the first component and the other one, and that's how it maps out the PCA one. I'm not going to go through it again because I think the code was much more clear. But the main thing is that the PCA solve our problem. So, well, not exactly. So let's come out to our main notebook now. which is that we are going to compare all of the approaches that we learned and try to see where we stand. Just give me a sec. Let me just clean it out. So this is the comparison notebook that is in the source. You guys can refer to it, and whenever you want, of course, in the future as well, just let me know. Dimension reduction. So here as well, we import all the things that we need, including, excuse me, pardon me, PCA, TESNI, UMAP, and the LDA. LDA is something that I just want to show as a means that it can be useful as well. So this is the data set that we're using. It is a data set that that is used in the American Sign Language. So we have overall all the alphabets and the numbers there. We are going to train it not train basically. We are going to just use the data set, which has 25 unique labels. And for the sake of GP, as I mentioned, I'm just going to eliminate it and keep 10 labels rather than all the labels we have, because I don't want to burn the CPU credit and it will take way too much time for us to plot it. Now, to make it simpler, because we don't want to again go through the same function, I'm just going to plot the functions of how we plotted as 2D. And remember, I mentioned that humans, we are much more used to looking at a 3D dimension. So we will also map this time in a 3D dimension all our outputs. The first thing we have to do is standardize our data, because data set, I mean, especially this data set, it is a bit weird, let's say, in the sense that for all the data points we have, sometimes we have more data, sometimes we have less. So sklearn actually provides in the pre-processing a small scalar, standard scalar that provides us to standardize our data, which we immediately do, which provides us pretty fast. For PCA components, we go with the 3 because I want to show it in the 3D as well this time. We make the fit transform and we just provide it with what we want each of the component to look like. That's it. Now we plot it in the 2D. So let me actually increase. I will decrease it a bit because so it will be visible for everyone. So this is what our data set currently is. It consists of different sign languages, completely cluttered out, which is we have no clue of knowing whether this symbol, this sign language is different than this or this. If it is, then by how long? So as it is pretty much clear with, as it is pretty much clear that we cannot distinguish even 8 and 7 here because they are way too cluttered out. That PCA is not something that we can potentially use, but that's only for the 2 dimension. What if we shift our data into 3 dimension? Would that give us any idea? Let's give it a try. In 3 dimension, we unfortunately suffer from the same problem, where even in 3 dimension, we are not able to distinguish between them. In fact, in 3 dimension, some of our points are more closer than they should be in the 2 dimension, which means that PCA is not exactly that useful when it comes to our visualization in this case. The takeaway from our experiment is quick one, that it is not good at differentiating signs. Obviously, we cannot see which signs are different. It is influenced by the other. When influenced, as you may recall, that PCA relies on the different point, actually the reference of the other data point from itself, which is why some of the data point are closer to when it should not be than its own original one. And as it's a linear projection, it does not capture the nonlinear redundancy. As you can see, it's completely linear. We do not have anything that can be classified as nonlinear in this case, even if we are going in the 3 dimension. So let's go for the TESNI now, because we studied the PCA. Now it's good time to see whether the TESNI actually stands it or not. The thing about TESNI, remember, is that it's computationally expensive. So that's why I'm restricting myself only to 50 here. So I only want 50 features to be considered, and that's it, more or less. I'm fitting it in with the 3 components, so 3 dimension for us with the TESNI. And for TESNI to work, it is also important to note that you should not be using TESNI as on its own. It's better that you first do a linear dimension reduction, which is something like PCA or SDB, and then come to TESNI. So that's why we are here reducing our PCA first, making it to 50, because TESNI can handle it, of course. And then we are inputting it as an input for our TESNI model.
Sir, can you please zoom it?
Yeah. Oh, pardon, sorry. I keep forgetting. Just zoom out when I'm on the diagram, because that will be then clearer. So here for TESNI, I'm just putting in the random, so it's a random number. You can choose whatever you want. I want it to represent in 3 dimensions, so 3. Verbose is basically in case you want to see the output that it goes by. I don't care, so with say 50. Perplexity is of course something you all are aware, so I won't go in detail for that. I set it as 40 for now. And the number of iterations, which is the number of times I want my TESNI to go through the data set and iterate, is set to 400. It's a random one. It depends on the data set as well. As you go by, gain experience, you may even have a develop intuition of how much iterations do you want it to be. Sometimes it can be low. Sometimes you do actually need to do it repeatedly in order to make it much more fitting. So we are done with it. It took 45 seconds for us. Let's plot it out, and let's zoom out as well. So for this one, it is a bit better than PCA because at least we can see a somewhat clusters forming, not precisely, but you can still see that there are somewhat clusters being formed around it. We have the some of them that are cluttered around, of course, some of them that are completely different, and so on. So let's map it again also on the 3D because we want to see how it looks and how to interact with it. So when we do that, we have a 3D map, which is still not exactly clustered, but at least there are some clusters being formed. Basically, in TESNI, if you see that there are some sort of clusters being formed, then it is a good idea to start playing with the iterations and the perplexity in order to see if you can actually make it fit. But it does not work in all the cases. If it does not work, it's best not to play more in it because you will then end up with overfitting your data and creating actually the noise that did not exist. So in this 3D one, we still do not see many more clusters. We just see some of the potential clusters being formed, but that's it. Which means that takeaway from our this one is that it does preserve some sort of cluster, some sort of topology. So let me zoom in. It does preserve some sort of topology for us, neighborhood, as compared to PCA. But because there are some of them that do not exactly provide us with information, it may not be the good to each other. And of course, something that, as you may see here, is that, let me zoom in actually, that some of the data actually overfit onto each other. So they overlap onto each other despite being separate, which is something that may not be good if you have features that require, even if they're similar, features that require to be distinguished from each other. So let's go to the something that is UMAP, which is something that has been quite prominent in our other experiments so far. So UMAP has, of course, 4 different main metrics that you have to set. One being the number of neighbors that you want to control, which can be low value, which if you set to low value, focuses on retaining the local structure, and the high value, which is on the global one. Then the minimum distance of how tightly you want your data to fit in. This, of course, influences what distance matrix you also use, and the n component of how many reductions you want, of course. And the matrix is the distance computation that you want. If you do not specify anything, by default, it will always go for Euclidean one. So we reduce our data set to the one that we want, we fit it in, and let it run a bit. It will take a bit of time, so it's UMAP. So let's meanwhile jump to our slides one. So we did the PCA one, we saw that it does not solve the problem. It's too cluttered, not exactly something we want to go for. Even in 3D, it's too cluttered out. There are barely any clusters formed, which means it's not useful for us. Even if we zoom in, it does not make much sense for us because PCA, of course, does not consider that to be important. Oops. So let's go for the TESNI results that we already saw. So TESNI, of course, takes high dimension data and reduces it to low dimension while retaining as much original data as it can. It was originally proposed by Martin and Hitton in Netherlands, actually, that tries to cluster the TESNI data as much as it can. But it's not exactly useful either because each of the data point has a reference point that is on the dimensional map, and it tries to preserve as much embedding as it can. In our experiment, of course, we already saw that it is not exactly an answer because it's still cluttered around. We still don't see, we see clusters starting to form, but not exactly clusters that should be appearing. Even in 3D, for instance, we see that the cluster, this is, by the way, the full data set. I have restricted it to 10 because I was able to do it on my local GPU, which was pretty much good enough. And you can see it's still not clustered. It still has too many variants or too many outliers around, not useful for us. Then we go finally for the UMAP one. So this is in fact a great website that I would refer to. It's called Pair Coding GitHub that has a brilliant explanation in understanding the UMAP. This is the MNIST fashion dataset. As you can see, they have mapped it to different dimensions and including the depth of each of the features. It is, of course, applied as a sparse matrix, and it eliminates the need to apply the reduction techniques that we apply for TESNI, which in our example we use the PCA. It is almost similar to TESNI, but it is a high processing, has better visualization, and tries to retain as much dimensions as it can. So we should have our results. Let's go there. Perfect. So we have our fitting done in for UMAP. It is fast. It's 18 seconds as opposed to 43 for UMAP. TESNI, sorry. So let's see our UMAP. Oh, too short. So in the UMAP, we can see it is kind of forming some clusters, not exactly still useful. But one of the reasons why it is not useful is that we are still in the 2D plane. It is in fact a bit more visualization if you go in the 3D one, where we can see that they are actually separated from each other by a large distance, in fact, not just a small distance. There are some, of course, that are close, which of course the reason would be that we have low number of data here that we are using. But if it is high, then potentially we will actually see a full set of clusters forming. So if you go back to our slides, in fact, this is for the full one, 2D plot, we can see some forming. And in the 3D one, we see actually some structures getting formed in, which means that UMAP is actually a bit better than at least TESNI or even the PCA in order to give us information or visualization for our data. So let's go to the notebook again. Clearly, UMAP did a good job at separating the points from the others, but we did not get any significant cluster. For instance, we cannot exactly say that this is one cluster because I can still see that there are some points that are close to here. For instance, the red one here in this case. So we cannot exactly claim that it is creating a significant clusters for us. The takeaway from that is that obviously it outperformed the TESNI and PCA. PCA took 38 minutes, TESNI took 52, while for UMAP it only took 18 seconds for us, 18.1 seconds, same seconds for us. It is faster than TESNI, and it is visualization. It's effective for visualizing potential clusters with their relative proximity. So which means that this cluster is potentially closer to the clusters of this one rather than the data point. So global structures in this case. The final one that is important is, of course, the LDA. So LDA is linear discrimination analysis. And what it does, that provides the data into lower dimension spaces with the good class separability. And the best thing about LDA is that it avoids the overfitting problem that we see, which means it tries to fit the data points on top of each other and the computational costs that are inherent for UMAP and TESNI. So how it does it?
Hello.
It is hello. Yeah. Hello. Did someone say something? Okay. If anything, don't hesitate to stop it. So LDA is one of the most commonly used reduction techniques, actually, that is mostly useful for pattern classification. And of course, when you're visualizing the data, pattern classification is the most important thing because that's what you're doing, right? You're classifying your patterns, trying to find some sort of pattern within your data set. For example, the PCA in this case works on the component to maximize the variance, while LDA works on maximizing the components axis rather than the data axis, which provides a clear class separations for us. It's almost similar to PCA in terms of its mathematical explanation or mathematical model behind it. The difference is that rather than finding again the component model for the data point, it tries to find for the classes or the clusters that are already formed, which is it tries to form the cluster, and then for each of the points, it tries to go ahead. Think of it like a KNN neighbors problem. In fact, neighbors algorithm is similar to that, just on a bit of higher plane. And of course, it is supervised learning based, so that provides us the maximum separation between the axes. So let's run it. We have our LDA. We are again going for the 3 dimensions because we want to visualize it. Then it's trivial enough to visualize for LDA. And if we happen to see for the clusters that are formed, wait, I resetted it. Yeah, as we can see, it is actually much better at clustering. It has been pretty much precise with clustering all of them. There are some points which were not, of course, clear. There are some which are outliers for us, out of distribution for, in this case, for us. But otherwise, it has been more or less pretty much clear with providing us with the clusters that we want. But this is only for the 2D. Does it still retain in the 3D one, which it technically should? So let's give it a try for the 3D. For 3D as well, we can see it has clearly provided us a distinguished difference between different clusters. Even the one that we in the 2D, we were thinking that they are not clear enough. They're still cleanly separated from each other. They're close to each other, but still separated enough to be able to form a cluster. And that's where we have the conclusion for the LDA, that it is faster in terms of computation. It outperforms all the other techniques that we have used. Remember, for others, we were taking more than 10 seconds for each of them on an average, while for LDA, it's literally 1 second. And it is not difficult. So, okay, that is one. So let's get back to our presentation. We also saw for the 3D that it is pretty much clean enough to be able to see the clusters and separation between them, which is what we are looking for, being able to visualize the data based on its feature directly. Now let's compare it. We have all 3, we did all 3 of them. PC, of course, was not able to do it. It did the most terrible job because we cannot even see any sort of difference between them. TESNI does a bit better job because it provides at least some sort of separations between the data points. UMAP, on the other hand, outperformed both TESNI and UMAP, TESNI and PCA, sorry. But it still did not provide us the clear cluster. It did provide us a potential structure, which means if we have a data set and we can analyze it further, we would be able to distinguish one cluster from the other, the data points between them. For LDA, on the other hand, it was clear cut. We were able to completely outperform all of them and able to understand it. So that begs in the question that why is that the case? Well, it's not surprising because the TESNI and UMAP are implemented without knowing the knowledge of the label. While LDA, for instance, it does has pre-knowledge of the label. We use directly the raw data, so it is capable of understanding the labels and directly going ahead with it. But that's still a question, right? Which method should we use? The answer, unfortunately, is not easy. There is no one technique that is better than the other. All the techniques are contextual to the data set you have, which means, of course, first always understand what your data set is about, understand what is exactly your need, what is the visualization, and the most important, understand the features and its importance or influence on other features. For example, the features such as age or your job we are doing directly influences the amount of money that we potentially spend. And that is an important feature, which means it should not be dropped out. There's no way to, of course, map a high dimension data to low dimension while preserving whole structure at the same time. No matter what we use, UMAP, TESNI, or even the UMAP Plus that came, I think last year was the paper, if I'm not mistaken, we cannot retain all the data. There will always be some or the other data that we lost. There will be some structure of the data point that will always be lost, which means we need to be careful when we are mapping that. So let's get back to our things here. So that's more or less for it for the talk, which means that we know that LDA perform all the others. Always remember, never fall in the pitfall that one method or one methodology is better than the other. There will always be some or the other caveat that you have to consider, especially when you consider the data set that you have, which means you need to consider the trade-off for your data set and your needs before you go for the visualization. And that's it for our talk. So what are the things that you can do now? I highly suggest all of you to try the code, change the data set, but remember, understand the data set first, then run the code. Try to fine tune the parameters of your visualization. For instance, as I mentioned, UMAP currently has different distance metrics. I only use Euclidean, but try it with Euler distance, Euler distance, or try with Manhattan distance. Do you see any other change? Try to see that. And apply the reduction techniques, of course, to your projects and share with me. Of course, I'll be happy to see them or answer your questions in this. And that's all for my talk. Thank you very much. I lost the connection.
No. Sankalp, we have time till 5 p.m. So 1 more hour we have. So maybe you, the participants can ask a question, and you can also like.
Yeah, please.
Yeah. And so like this PCA and all that, if you can demonstrate it little slowly, then as you.
Yeah, we can do that. Yes.
So that also we can do. So, but let us check if students, if participants have any query or anything they want to show, want you to demonstrate properly, and then we can go ahead.
Yeah, and we will go through it again. Don't worry. The thing is, I mean, I thought that there is always a break in 15 minutes. I was like, we are going to stop and do it again.
No.
Have you shared that this code, Shankar?
Yes. So you can go to the my repo directly. I will also share the slides with everyone, and visualization workshop, and you will find it there. Let me put it in chat. I think the chat is on now. So each of the labs notebook, sorry, has also collab link, so you can go there and try it directly. Just something as a point for everyone. If you're trying to try for the UMAP, make sure that you do not go for more than 10 or 20, unless you are planning to use your GPU credits on the collab, because for more dimensions, it will require you to have a credit card and use the credits from Google. So feel free for the questions. Otherwise, in 10 minutes, we can go through again all of them. Oh, sorry.
Sir, can you share those links with us in WhatsApp group, because chat box is not accessible to participants?
Oops.
We'll share
it on WhatsApp. Yeah.
I will take it from Sankalpa and we'll share on WhatsApp.
Yeah, please. Thank you.
Okay, nice.
Actually, this dimensionality reduction is very important topic. Whenever we do with machine learning, and for example, Sangeeta madam was also explaining, she has a 52-bit vector, so there were 52 attributes. And yesterday also Ambuja madam has explained one data set where there was around 50 plus attributes. So a human being cannot visualize a data which is so wide, more than 3-4 attributes. So it's always good to find out more significant attributes.
Mm-hmm.
So identifying the most significant attributes is a key part of any research, which is where machine learning is involved.
Mm-hmm.
It has a means lot of burden when the number of attributes are more, so it has a burden on the model also. So therefore, if it is this, then it's always good. And this all methods which Sankalp has explained were are very useful, and we can think of which will be more suitable to our problem. And it's better that we already get some code from Sankalp, like he has developed it, and then we can use it. So make sure that you understand it well, so that your efforts in your research will be reduced. So there will be
In fact,
reduction.
I can
Yeah,
even
okay.
give like a short example. Recently, I mean, literally last week. So we are currently working on the project, research project, where we want to identify the bug reports that we get from developers and being able to pinpoint the issue where the fix potentially can be. The problem with that is that the person I was working with is not from machine learning background. So they were treating machine learning models as a black box, which is something I see many people doing. And that's something that should be avoided, because you throw everything you have and hope that you get answer. The problem is that you overfit it, which means you have too many features. So you get false positives a lot. Second thing is that you do not actually understand what the problem was. For instance, one of the bug report even said the problem was in the README file. Like, that doesn't even make sense. So that's when we had to go back, reclean the data. And then we understood that, no, we need to only use this feature, not the other. And for each of the case you have, remember, pre-processing is not just about cleaning the data. It's also about applying certain techniques, such as camel case. For instance, let's say you have an NLP-based model, that NLP-based data set. So make sure that you are deciding first whether you should go for stop word removal, whether you need to have a camel case removal or not. And for each of them, the order also matters. For instance, in the bug reports, we found out that if you have camel case and then you go for the stop word, the accuracy decreases. The reason being that with the camel case, you're removing just certain things, but with stop words, it actually influences the camel characters. So it's better that you remove the stop words first, so that you have a cleaner camel case processing to do, and that provides you better accuracy. So always remember that there are too many things that you need to consider. And something that I always also found a bit funny, and I must admit that I was similar when I started my project with the BGL the bank. I was hired as a data scientist, of course, and my thought was, okay, I'm going to design awesome model, going to have awesome results. So when I went in, I realized that designing model literally took 1 day for me, but it was the data analyzing and pre-processing that took 3 months for us. Actually understanding what the data was, cleaning it, making it compatible with our model is what is important. So machine learning is 90% of deciding what 90% is actually cleaning the model. 5% is deciding which model you want to use, and 5% is the computation. That's it. That's something I really learned. And that's a lesson that I think not many people are aware of, especially when they come to industry. They think, okay, they're going to design awesome model and that's it. But that's not the reality, unfortunately. So if there are any questions, please feel free. I mean, you don't have to restrict to just data as well. If you want any other information, including for something that I might have experience already, I can share. I would be happy to share it. If not, of course, we can go through the code again. I can go in detail again. So we can go through the code then, I guess.
No, let's wait. Like
Okay.
people think and then ask questions.
Yeah,
So
true. I hope I was not too fast though.
the mathematical concept of
Yeah, I actually wanted to avoid the mathematics because it gets then too complicated to explain.
yes. So that's what I was about to tell. Like people like me also afraid of mathematics. So
I'm also.
we generally avoid PCA and all this. But it's good
Yeah.
that when there is a model for us, it's easier task. So just go and apply. But it will be good if you just step by step show how actually it works, and then it will be better for us. But let us wait.
Yeah,
for
that's my plan for the last 30 minutes. So no worries.
Yeah, but let's wait for a few questions. Like if it is like someone's research is like that one and it can help pull to him or her, then let us wait for some question.
Yes, or even if you have any questions about data set, because most of my projects required me to actually hunt down the data set myself. They were not clear, like what exactly should I be using it. Like I was not allowed to directly apply my models on the bank data, it's sensitive. So I had to create dummy data sometimes actually take the data that exists and modify it myself. So if there are any questions that you people want to have about any sort of data set that you want to look for, also don't hesitate. I may be able to find it potentially.
That will be also a great help, like because standard data set, and then you can, like if you have some tools where you can generate your own data set, that's again a very good area which will be of help.
In fact, I mean, after the talk, I can send an email with all the references as well I have, especially for the dataset generations. Although most of the dataset I know are from either banking, which means financial dataset, dummy dataset, of course, some of them that we ourselves created, and some of them are the source code dataset, so software engineering.
So if you have any question or anything you want to ask, then we can discuss on it, and otherwise I will ask him to show.
I'll go through the. And of course, if anyone is trying it immediately, feel free as well. And if there is some question on that, I mean. And of course, if anyone is interested in mathematics, I will send the reference.
Okay, all right. So we can show this PC. Actually, let us stick to one model, and then you just demonstrate how it works. Like the number of attributes initially, then you reduced it, and then how it is being reduced, and how many attributes remained later on, and how the significance has been identified or understood. So that's how we can go. So step by step, it will be easy to understand.
Yes, perfect. We can go each step as detailed as we can. Which one would you like me to go?
Yeah, it's much known.
So TestNI or PCA?
Yeah, whatever is okay for you, can just go ahead.
No, both are fine. I mean, both are good for me.
PCA will go with principal component.
Okay, PCA. Okay, perfect. So yeah, just to refresh again our minds.
Zoom in so that everyone can read it.
Yeah, true. Is this okay?
Yeah.
Perfect. So yeah,
so
just to refresh again.
Like whenever you will explain like the code at that time also you just go slowly, so that step by step.
Yeah.
One model we will understand very easily, clearly, and then we will revisit your video so that we can see the comparisons.
Yes, we can directly do it here. Actually, we don't even need to compare. I can compare it here. We can compare it here. Okay. So yeah, well, the goal of PCA is, of course, to reduce the dimension of multi-dimension data. And PCA is kind of unique. It is the only known, or let's say the only one that is used, because there are others, so I should not say the only known, that uses linear model that works on linear algebra. What it does is that it method of finding the axis with largest distribution of variance between the data points and projecting it on the second axis. So which means that if you have a data point on the first dimension here, it tries to put in the gradient for that, compare it for the other one, and create a sparse matrix, covariance matrix for that, which all of us know, calculates its eigenvectors and eigenvalue compared to each of them, and accordingly map them. The problem, of course, is that it is difficult to intuitively interpret the generated two axes, because it's always a problem. Everything kind of fits in over each other, especially for matrices. When we see them, when we see it for two different data points, it may not always lie on the same one, so it's hard to understand. The disadvantage is, of course, because of this, the cluster data is completely on top of each other, or actually overlapping each other and even crushing it in some instance, as the dimensions are reduced to make it linear. We cannot, of course, I mean, I'm sure all of us probably in the physics class of our 10th or so on, we always had the problem where we had, no, not 10th, I think 12th, where we had the Green's theorem, where we are supposed to reduce the dimension of 3 dimension to 2 dimensions vector. And that is always a problem, right? Converting anything from higher dimension to lower dimension, we tend to lose certain information. And in case of PCA, it is not just lose, it's actually completely crushed out. So let's do code step by step actually. For imports, we're using the NumPy. So NumPy is, of course, a famous library that we use to represent tables, so to show the tables of our data and to read CSV file. There are other packages as well, such as CSV, but it's not as useful as NumPy, which also is used for numerical computation. Sorry, my bad. NumPy is for numerical computations for higher degree. So if you happen to in Python do 7,000 multiplied by something ... then it's going to be a bit hard for it to interpret with the precision. But NumPy technically allows us to bypass it. Furthermore, NumPy also allows us to do matrix computation if you want them and other sort of mathematical things. Then we have the pandas. So pandas is a famous library that is used mostly for data manipulations. So if you have a CSV file, XML file, or those kind of files to read through, you prefer to use pandas. The other alternative is, of course, I will just write it here. It's CSV. That is used as well, but it's not as flexible as pandas. The reason being that pandas actually loads the data in the memory as much as you want, which makes computation faster. While for the CSV, you actually had to manually open the file on the OS level and read it line by line, which means it cannot remember the pointers there. So it's pretty slow. Then we had the matplotlib, which is, of course, to plot our mathematical graphs and plots. And this is just for the sake of collab, that we ignore all the warnings that are there, because there will be warnings that we need to update this or that. So we can ignore it. So let's start with setting up our configuration. So these configurations are not purely relevant to PCA, rather they are relevant to how we are mapping our PCA plots. Of course, we don't want just a random image coming in, so which is why we are setting our CMap. So image.cmap is a parameter for RC parameters for the plot function of a matplotlib. We can see it here. It's a state-based thing that provides a way of plotting it. And we are just setting it as a grayscale, so which is the background will be completely gray, allowing us to be visualize it much better. You can change it to other things as well as you want, but we can come. I can show an example afterwards for that. Then these are some random set of colors, so basically RGB and their own spectrum that are set in, so that we can visualize our dataset better. If you do not put any dataset, the matplotlib will actually randomly take the colors and plot it for us. The only reason I'm setting it here is that to make it easier for us to compare with other things. If I set the number for 1 to be this, 2 to be this, it's easier to see when we have a comparison. You can set it either as a name. Of course, you can write literally red here. I don't know which one is red actually here. You can write it red, yellow as well, but I prefer the hex code because they're a bit more precise. So the first thing we have to do is, of course, load our dataset. So here we're going to use the MNIST dataset, the number one. So we provided our variable, we do the read CSV. So this is pandas. So pandas has a function called read CSV that allows us to read the CSV file. Remember, it only works for the CSV. If you want to have, for instance, a TSV file, which is separated by tab rather than comma, which is what the CSV does, then you have to pass in the parameter, which is called delimiter, and put a tab there so that it will always read it correctly. The mnis.head actually provides us with a sample of dataset, because remember, when we load our dataset, we also want to see what the dataset is like. So just doing a dot head provides us with the information of the headers, which is these ones, and left side columns, and a small set of data to read through so we can understand. So the data here is labeled. So this is for 1. So the 1, how it is written, it is represented as multiple pixels, which is the number of 784 pixels are used to represent just 1, and each of them is a Boolean value 0, 1, 0, 1. So where we have 1, that represent that this pixel is active, 0 means the pixel is not active, and each of them represents one figure for us. So we want to, of course, I mean, when we are doing it, we don't care about labels at this point because we are doing PCA, so we don't even want it to be supervised. So what we do is that we load the label. So we consider the labels as label column. We put it inside an array of label, and we drop the label column directly. And in place true means that we replace it with nothing and just create it as a first access for ourselves, which means when this is dropped, it doesn't keep an empty column, rather it just squashes it, which means this column is completely deleted like in Excel. the A column gets deleted, everything shifts B to A, C to B, and so on. Now, we have done our cleaning and everything, but we want to know what is exactly the data set. I want to visualize it so that I can see my results and compare it against it. So for that, rather than going in elaborate thing, I basically just wrote a function which I call array to image. What it does is that it takes an array as input. Array in this case is one line, one row of our data set, and converts it to the image of size 28 by 28, and it returns the image.
Are there? Like, how many objects?
Sorry?
How many objects are
array. We have 700 more than that. So each of them has different way of representing, and there are 800 pixels to represent. So we can actually do it. Let me show you.
You share like here in different browser, if you can see that.
Yeah, I don't think you can see it on different browser, but I can just put it here.
No, it's okay. Yeah, here also. Like because we have seen only 5 objects as you are using head. So like how many objects, like how many images are there?
It is showing 5 rows only. That's why.
Yeah.
No, let me show you directly full one.
Complete all.
It is showing only 5 rows. That's
yes.
Head.
So,
Due to head, it is showing 5 rows.
One as well. So this is the full data set we have. Of course, it's compressed again because otherwise the Google Colab will crash. So we have 4,200 rows. Ignore the first one because that's
42,000. 42,000.
42,000. Sorry.
Okay. So it's a big matrix, 42,000 by 785.
Yes, 784 because we stripped the first one. We don't care about the first one.
Yes. So 784. Yeah.
Perfect. I can print as well the image, I think. Yeah, I will show you a quick image afterwards. So here, of course, I mean, first we convert the array, so which means each of the row as an image because we want to see how it is. And it is 28 by 28, which is the size for it. And we put it as a subplot for us. Now that we have our plot and everything, we want to iterate over our index, which is the label, and the items for the array. So we basically parse on our function, and inside that we pass the MNIST data set with the index being 0, starting from 1, and index plus 1, which is we are just doing it 1 plus 1 plus 1 for each of the values. For each of them, of course, we add the index label. So the label that we have here as a index as a title for that. We can change whatever we want here, and we don't care about the other axis, so axis is off. And finally, we plot it out. So this is what our data set is. This one is 1, it represents 1. This is a sample of it, of course. We have 0, how it's represented. We have 1, how it's represented, and so on. So this data set is purely just number pixels. And of course, we just map it out to see for ourselves how it looks like. Now we come for the PCA, which is the normal. So for that, we use from sklearn the decomposition, under which the PCA lies, and we import it. We set the number of components to be 2 because we first want to just set our dimensions to be 2 in this case, and we make it fit. So fit, of course, as we discussed earlier, is just an inbuilt function that allows us to fit all our data within PCA matrices in this case, and actually make sure that it is consistent with what we have. After that, we just make a transformation. So what transform does is that it applies the dimension reduction to whatever we provide inside. So in this case, we are transforming our MNIST data, this data, to be transformed as a PCA. That's it. I mean, it does it for itself. We don't need to do anything after that. After that, these are just a set of functions that I generally always use for my other projects as well. So I just pulled it from there, to be honest, which is that I'm just plotting as a plotly. So plotly is actually one of the inbuilt function of matplotlib that allows you to make interactable graphs so that we can scroll in and actually interact with each of the components we have. So I set it as a figure, and of course we have to iterate over it. Earlier we fit all our data. Now we need to make sure that each of them is pointed as a scatter graph for our mapping purposes. So we go for the scatter, of course. We provide it with the MNIST, the input of our transformation. We provide it with what it's supposed to be and what its label is supposed to be. The label is, of course, the first one we have. Then we do the same for the Y, and we provide the name again as an indexer label that is there. We provide the markers. I mean, we are, of course, putting it as a marker. We don't want it to be too much transparent, so we're putting it as opaque. And we are putting it as, again, the colors to be similar to what they are as their own index. Once we have done that, once we have iterated over it, remember, I'm only limiting myself to 10. We can do it for the full one at the end. Then we are just updating our figure because we declared it here. Now each of them needs to be mapped in correctly. So for each of the iteration that goes through, we put in the PCA results and map all the results that we have. And when we do the show, which is the normal command, it will automatically provide us with the information of our data set and the plotted one. So this is for the 2D. Let me just pull the command from the 3D directly so I don't have to rewrite it. Actually, let's do it here. We don't need to map it. So we did it for 2. Let's do it now for the 3 one.
Now can we see that like after applying PCA, the revised data set, like here the objects will be 42,000 will be as it is, but the dimensions will be reduced, like how much it is reduced.
Okay. We can do it here ourselves. Oops. Actually, let's do it here. So this is because it transforms it into NumPy array, so which is a specific array that is used by NumPy. So if you happen to run it locally, you will see a file called npx, I think, that is generated in your where you have the code. So this is how each of our array represents now. We cannot see, unfortunately, the dimension in this case because it will require us to actually go inside the decomposition and change it out.
Okay, but when we show, when we see the graph, so it has some 8 or 9 attributes, or that was a different one. When we see
this one,
yeah, it was like this 8, 9. What is that up? These are the
these are the labels.
Labels, okay.
So these are the labels because this is what the 4 represents, and for each of them, I mean, because we have the graph object, it provides us with a kind of highlighting to see which one is which one.
Okay.
So we can remove them just to be able to see it, but to be able to retain it as a output for us, we will have to go through the NumPy array, iterate over it.
Okay. So as you said, like it crush actually the data and then it generate a new matrix.
Yes, which is why we say PCA is kind of bad in this case. Yeah, because like, any sort of crush data, it removes everything, any information, useful information that we have.
Okay, we cannot undo it like as it is.
No, unfortunately no, because once you have folded any data, you don't know when to unfold it, where to kind of unfold it, right? Once you have projected it, you will have to redo it from the scratch in order to be able to change it out.
As the same is true for Disney and other?
Not exactly. For the UMAP, the good thing is that it tries to retain as much as it can, which means that if you store it, just give me a moment, please. Did I mess up? If you happen to change your UMAP, I mean, when you're making it in the fitting model, if you happen to store it, then you should be able to still retain the original information. The good thing about UMAP is that it actually, for instance, let's put it here. It's the same one actually, so I won't change it. There are some libraries that actually allow you to retain back the information about what was the fitting of it. But once you have fitted it, it makes no sense to go back to the data because we are purely focusing on the visualization. If you're looking only for fitting the data, I mean, only for transforming or reducing it, then you should just use your reducer with whatever function you want to be able to output it out. Just a second, why is there error though? Because I did not select enough data. Yeah, that's fine. And remember, so when you want to, for instance, pass on your dimension reduction for any sort of machine learning model, you should not be using them as raw, which means how we are using it. If you're planning to use it for any sort of model, then your reducer should directly be the input of the model reducer, because each model requires different set of, not different, I should say, but its own specific way of fitting in the data. So depending on what you're using, for instance, let's say you're planning to use CNN in this case, then your CNN will actually provide you with a reducer and an inputter, which will map the data from whatever fit you have done to its own format before being taken inside. Just give me a minute. I'll just grab some water, please. Yep, sorry for that. For reducer, there are other parameters as well that you can use for the UMAP. For instance, the number of neighbors that we want per component, we can try with that. The number of, okay, my keyboard is acting up. The number of components, of course, which is the number of clusters you're more or less, or dimensions you're looking for. If we keep it null, then it's fine. The metric is by default always Euclidean, which you can change, of course, to Manhattan, for instance. Let's try it actually with Manhattan. See how it is. Euler, I think. Better. Okay, Euler is not there. Let me check, because I don't know which one available in build. So these are the documentation, really nicely written. So it's always a good idea to go through that. Let's see metrics. So you have Manhattan, which is the Minsky style. There are also other ones that we can use, but these are generally not recommended, especially the correlation one, unless you're reducing your data to completely low dimension. So let's try Manhattan for now. I think it's supposed to be single quote. No. Of course, it will. UMAP unfortunately is quite slow, so it always has some issues with going ahead. Meanwhile, I can quickly show something else here.
Yeah, I was talking to you, Sankar, like if you have say for 50 attributes, so instead of extracting then crushing it, can we find out which one is more significant? Like if we get some significant value, significance of each information.
Yeah, we can actually apply. I see. Okay, we can actually apply the significance one, but I'm not sure which one can be applied here. Generally, what we would do in case of, for instance, where we are limiting ourselves to something, is that we would trim our own data set, which means rather than representing it completely. What is it? Trim? I think no. Wait, need to run. What can be done generally, I mean, is that use pandas, which is what we use, and trim our data set so that we don't have to use all of them.
Okay.
But since in this one, we do not know the significant features, and I'm, to be honest, not much familiar with how to exactly choose the significant features unless it's a data set you know. So for example, let's say in our case, this is unfortunately not the best data set, and I was not able to find any good one. I found one about penguin, but it didn't work for me.
There are some metrics, like say we use generally information gain, and then other Gini index also is there. So that also helps us to find out here.
Yeah, but that only helps you when you do not have too much knowledge of the data, because it tries to approximate it. But better idea is that you yourself do it, which is, for instance, the example of the banking one, for instance. Let's say I don't have any use of what the person's tax ID number is, for example. So that kind of thing, it's better to trim those. So you already have a data that is already reduced or compressed with only the meaningful information. So when you happen to put any sort of manifold learning, it will still retain the information that is useful rather than creating noise with the irrelevant one like the tax one. So that's something that is done, yes, but I'm not sure about any, let's say, significant finder in this case, unless you treat the machine learnings as black box, which is what we generally used to do, but it was not performance efficient, frankly.
All right.
So we are done with Manhattan, I think.
Okay.
Yep. So let's try with the Manhattan one. We need this. So for Manhattan, we have a bit different. Let me actually put a label here so it is much more clear. This is the Manhattan one, and we'll quickly run a normal one as well with Euclidean or other distances, just to see how it affects. And remember, for UMAPs, it does affect pretty badly. So let's go for cosine actually, because that will provide probably more information because it will be completely folded out. So that is also something really useful to check before you jump in anything, that which distance do you wish to use for. In most of the cases, I mean, generalizing to almost everything that we have worked on so far, Euclidean is the best one that will be used because you do not care about anything else except understanding what your data does or visualizing it, for instance, for management to see.
Okay, all right, that's good. And any tool you can just show for data generation like that will also.
Unfortunately, they are the proprietary one, but I will send some freelance one, sorry, open source one that I have, which provides you with information of generating data sets. Something that I cannot recommend enough actually is something called, yes, this one. It's a repository actually that consists of different data sets that you can directly use. Most of them are freely available, and they are in fact what we also used for initially testing our models for understanding the data before jumping on the main data set. So I will send the link as well on the email to Professor Joshi, and he can forward it to everyone. Most of them are pure data set available freely, more or less. So this is the Google one, of course, that we already know. But others, for instance, probably are the NASDAQ as well. I think is no longer available because they removed it last year. But there are still some that are available which you can go through. It is a curated list, so it is actually created by the community, most of them, and some of them, for instance, what is it called? Bench for BL. This one you can generate it yourself. So it is a data set that is actually for bug reports and fault localization. So it's something my colleagues have worked on, and the data set itself, you can do it, you can create it on your own. They have provided the tools for that. If there is some specific data set that anyone is looking, don't hesitate to ping in for that, because I would probably have either an idea or I can ask my people around here for that.
Okay, great. Okay, all right, Sankal. If anyone want to say something, then we'll have that one, and then otherwise we will stop.
Yep. Any questions? I'm open for that. Sorry for my voice, by the way. Just not used to speaking this much. And of course, feel free to contact me as well afterwards if you have any questions, or if you just want to have a chat about anything, any interesting projects.
So you mail me all the pointers so that I can share with with all the participants. Thank you very much. Thank you very much, Sankalp. You demonstrated the difficult part that we generally feel, the data reduction, dimensionality reduction. With you demonstrated with different algorithms, and thank you very much for that. I appreciate that you spent time, and then you created the data code also that we will share with the participants. Thank you very much. Thank you for joining.
Thank you very much for giving me the honor of talk. It was really great. And of course, to everyone, you're always free to contact me, not just for this one, but also if you have any other questions, including data analytics, or if you want to help with some code that might be issue, just ping me up. I'm always happy to assist.
Okay, thank you.
Sir, can we have your mail ID, sir?
Yes, so it's MAIL. Oops, let me screen share so it will be easier, I guess. So you can just say mail at sghatpande.eu. I will also forward it in the email with the slides and everything, so you can always ping in anytime there.
You zoom in.
Oh wait, I don't think I can zoom in here. Let me write it here. Yep, this one.
Yeah, fine.
Great. So thanks a lot, everyone. And I hope I did not bore everyone too much with, I tried to avoid mathematical details. So I hope that was good. I personally am not fond of mathematics. So.
Okay, thank you.
Cool.
Thank you.
Thank you very much.
So,
yes, take care.
yeah,
Bye.
thank you. Yeah. For participants, like tomorrow we will have 3 sessions, and then the first session will be from Nilesh Patil, who will be sharing us the tools that are used for, because the cloud, generally we are using nowadays cloud and many variations of cloud where we can put our data, vast data is there. So we can see how various cloud options are available for data science. That's one information, very good information will be shared by Nilesh Patil tomorrow. Then we have another one from Norway, Professor Akerkar, who will share with us some business intelligence tools and some other data about big data opportunities and challenges. So he works on European Union projects, many European Union projects. So he have the insight of big data and what are the opportunities available over there. So he will share with us, so we can connect with him. So it's a good opportunity for all of us who are working in academics and want to get connected with the European Union. European Union has many projects, so that you can get connected with him. So, and one more is we have to take one session which is on life values. So we have picked up one session that is called as stress management. So tomorrow we will have afternoon session that is stress management, and I assure you that it will be the best session. So you you will like it very much. So thank you all for joining today. We'll join for day 4 tomorrow at 10 o'clock. Thank you very much.
Thank you, sir. Thank you.